So we need a faster way of reaching the state, and now people have started using
This meeting is being
machine
recorded.
learning tools to understand. The moment you see a fraction, some part of a charge table taken, you can tell the machine learning that routine can tell you where to go in voltages. That's a lot of there's a lot of works in that. Generally, what is a quantum superness? What is the definition revised? How far is India from? It's kind of hard to. I mean, that again depends upon your which system you're talking about. Actually, yeah. So, how is useful to measure quantum vectors? How is it useful in measuring a quantum? Sir, how is it useful in measuring it? I didn't understand the question actually. How is it useful measuring quantum vector signal? Yeah, in for what? I don't understand that part. Yeah, I guess that's it pretty much what I have. Yep.
Yeah. Thank you, Professor.
Yep. Okay.
Thank you. Thanks a lot.
Okay. Thank you. Yep. Shall I log out?
Sure, Professor. Thank you.
Okay. Thanks.
Good evening, Professor Saptarishi. Professor Saptarishi,
Hello?
Can you hear us? Yeah. Good
Yes,
evening,
I can
Professor.
hear you. Yes.
Yeah.
Hi. So, should I share my screen?
Yes, Professor.
All right. Okay.
So we can see you.
Thanks. Okay, let me share my screen.
And your screen as well.
Fantastic. All right. Thank you. So should I start?
Yeah.
Okay. It's a great pleasure to be here. And first of all, thank you, Dr. Ram Shankar and everyone at the QC Hub for making this familiarization program a success. I'm really impressed seeing so many participants attending a Friday night seminar. And so what I will try to do, I will try to give a very brief and rather non-technical introduction to the neutral atom-based quantum computing platform, which is one part of the National Quantum Mission activities, what we are doing here. And so apologies to the experts, but I would encourage the candidates to ask as much question as you want. All right, so I'm just sharing the screen, some of our recent results. So if you are interested in more details, what we do, they will be contained in these papers. You are welcome to connect with us and ask question on those aspects. So let's just get started. When we say that neutral atoms or ultra-cooled atom, laser-cooled atoms, they are used for various quantum technology development because atoms are building blocks of the matter, and they are used to employ in various technology development as well. So it's not just limited to quantum computation. While quantum computation is one of the strong aspect, I have just taken a picture from a commercial quantum computer using neutral atom based quantum computing platform and shown this to scale to see that what this objects looks like. Some of the pictures from our labs also I'll show towards the end. And they are also used for quantum sensing and metrology. For example, magnetometry, where these atoms are used to measure magnetic field, RF fields, and many other fields as well. And then they are also used for quantum memory, quantum simulation, hybrid quantum devices, for example, also atomic clocks, and various other technology platforms. This is just a very small section of what one can do with this neutral and ultra-cooled atom. Just wanted to show the people who are behind this work in my lab. So we do have PhD and postdoctoral researchers, as well as research associate, research assistants, and also past members. And we also acknowledge the support from the National Quantum Mission, as well as core grant from DST and IHUB Quantum Technology Foundation, and previously from MIT as well. All right. So going further, the facilities what we have in our lab is laser cooled and trapped atom clouds, sodium atoms, potassium atoms, as well as rubidium atoms. In today's lecture, we will highlight mostly how we do quantum computing, or we are developing the platform for practical quantum computing using neutral rubidium atoms. So these atoms are trapped inside an ultra high vacuum chamber. You can see a fluorescence image of these atoms, a bunch of them atom, and then they are transferred into optical tweezer trap. These are focused laser light created from an hologram and then sent onto the atoms, and then one atom gets trapped in each individual lattice site, so to say, or the tweezer site. And I will explain the physics behind that. And then one atom which is trapped in one such, let me see if there is a pointer. Yeah. Right. Okay, pointer, laser pointer. All right. Okay, so one atom trapped in one tweezer acts also as a qubit. I will try to explain how these atomic qubits are manipulated as well. All right, so the plan of this presentation is that I will tell you about the basics of neutral atom-based quantum computing platform. Then I will tell you something about the basic technology, what is used here, which is namely laser cooling and trapping of neutral atoms, then optical tweezers and single atom trapping. Then there is something about both reconfiguration of this atom array into the traps, and then Rydberg excitation and entanglement generation. Then if time permits, I will explain how this gate operation and universal quantum computing as well as analog quantum computing is performed in this system. Then there are some technical considerations, various ones actually, depending on the time what we will have, we can discuss on some of them. All right, so just as an introduction, so we have this neutral atom based and trapped ion based quantum computing platform. I'm sure Professor Umakant Rapol have given you a nice introduction on the trapped ion based quantum computing platform. I will today focus on the neutral atom based quantum computing platform, which actually mandates a 400 qubit neutral atom based quantum computer using highly excited Rydberg neutral atoms cooled to a microkelvin temperature. And then we are also looking for hybridizing both atom and ion based system, as well as having both analog and digital platform, and then possibility of exploration of miniaturization of this system. I also wanted to highlight our neutral atom based quantum computing platform. We have given a name which is called Anvika, which has a strong Indianized connection, which the full form is Atom Network Versatile Integrated Quantum Architecture. And these are the team members, the key members of our team. There are, of course, other team members who are part of this activity. All right, so I just wanted to introduce the team of faculty who are focusing on the neutral atom-based quantum computing platform, and then ion and theory and algorithm platforms are also part of our activities. Okay, so this is how we are geographically distributed all over the India, the neutral atom and trapped ion-based quantum computing platform development. Now, getting into the technical details. So what you are seeing here at the left are a few of the tweezer positions where atoms are trapped. In the black regions are trapped atoms from our lab. And then these atoms here, of course, these are not yet single atom, a few of them cold atoms. But once we have one single atom in each lattice site, in principle, they are a qubit. I will explain how that is manipulated. However, there are many challenges. One of the challenges how to detect and image them in real time with high signal to noise ratio, as well as why these traditional techniques are a bit of a challenge, and how to address and manipulate this single atom qubit as well. So these are a few of the topics what we will be discussing today. I also wanted to highlight that globally there had been a lot of new progress. For example, QEra, which is a spin-off of MIT Harvard collaboration, and this is a commercial company who actually makes these neutral atom-based quantum computing platforms. And at present, they have 256 qubit quantum atom platform, which they are selling all over the world. And so this technology is already maturing, as well as Pascal, a French company, which is also doing the similar technology platform development, and so is another company called Inflection. So all these companies are invested in neutral atom-based quantum computing platform development, which is a great thing actually, that there is a lot of global interest as well in this way of doing the platform. And okay, I forgot about another company called Atom Computing, and there are quite a few which are coming up. Okay, so what are some advantages of neutral atom-based quantum computing platform? In many of the talks, you must be saying that when people think about qubit, they think about atom. And there are various other platforms where the similarity with the atom is what is highlighted and utilized. So one of the best things about atoms are that these are like natural qubits. So each atom is same in every lab. So who uses them and who is making them is not a question. All atoms can be used the same way. Though the trapping and manipulating is a little bit of a novel technology. So I will explain this. There is an all-to-all qubit connectivity, which is important. This is scalable. For example, number of atom qubits are relatively easy to scale. Actually, though I keep on saying that ultra-cold atoms, but actually the operations are at room temperature. All the devices, all the subcomponents are at room temperatures. The atom's kinetic energy is reduced to a level. That's why we call it ultra-cold atoms. But apart from that, there is no need for large cryogenic cooling systems, etc. There are long coherence times these atoms do have. They offer both analog and traditional digital computing platforms. So there are quite a few such things. Then going forward, there are some challenges I would not call disadvantage. One is this requires localization of each individual atom with precisely tunable interaction between atoms. This is the technical challenge. I will say how we handle it. Again, this technology is relatively novel. This field requires more R&D compared to mature platforms such as superconducting qubits. So this is one area where young researchers will find excited about, because there is a lot to contribute to. This requires complex laser systems to trap and manipulate atomic states, often consist of multiple optical components, making individual miniaturization and portability a bit challenging. These atoms are required to be trapped in ultra-high vacuum environment, because if these atoms are in room environment, there are other atoms who will knock them out from their trapped position. So that's another level of complexity. We are talking about 10 to the power minus 14 bars of pressure. So that is a very, very low pressure, which is not very easy to access. And there is a significant skill development and hands-on training required. So these are some challenges. So one of the first step is that in order to trap these atoms, you first have to make sure that their kinetic energy is reduced. So this is done via one process called laser cooling and trapping. So what is the process? So this actually takes down atomic velocity distribution from room temperature, which is around 300 Kelvin, to of the order of 100 or even tens of microkelvin, or of hundreds of nanokelvin up to few microkelvin. So that is one step. So this is based on radiation pressure, and this is evident in many other areas. When, for example, comets passed by sun, the radiation pressure can be seen as one of the tails away from the sun's radiation pressure direction, and that was observed long time back. So in case of atoms, what we talk about atomic energy level, so these are in terms of electron total angular momentum, and then they are classified as fine structure and hyperfine structure. Those of you who have taken an atomic physics course will be familiar with the atomic fine and hyperfine structure level diagram. So traditionally, it's a bit complex. The level diagram is particularly in presence of external magnetic field. However, this can be approximated approximately for a two-level system. So one ground state and one excited state. Once we approximate as a two-level atomic system, then one possibility is that if you excite an atom by shining laser light onto that atom, so it will go to an excited state, and almost immediately after some few tenths of nanosecond, it will radiate out, and then there is a sharp resonance. And then there is another concept, is that if the atom is moving towards the laser light, then the apparent transition frequency of the atom is shifted. This is known as Doppler shift, and that Doppler shift actually causes the atoms to be okay. I need to probably disable scribbling, and this is annotated. All right, where is that? I don't easily get access to that. Anyway, so let me continue. So utilizing this Doppler shift, now one can think, if you have an atom which is moving towards a laser light which is coming from the left, it sees the laser light frequency shifted because of the Doppler shift, and then it absorbs the laser light even if the atom is not on resonance with the Hello?
Yes, sir, you're audible.
Yes, okay. So there was, I think, some disturbance. It's okay. So can you tell me till what slide it was visible? This one was okay?
Yes,
Hello?
sir. Yeah,
All right.
previous one is.
Okay, so I'll continue from there. I hope so. Because of the radiation pressure on the atom, the momentum transfer from laser light to atom happens, and it actually allows for the atom to reduce its velocity. All right, so the spontaneous emission causes the radiation in random direction, which doesn't cause additional change in the velocity except for some small jitter, and that's why on an average there is a slowing down of the atom. Now, just imagine sending this laser light from two opposite directions. So if you can slow down from left direction, you can also slow down from the right direction. So that's the philosophy of cooling the atom down or slowing down the velocity from both plus x and minus x direction. And this concept can easily be expanded to 3 dimension, and then there can be a spot or a region where the 6 laser light intersect, where one can have a cloud of atoms which are cooled down to very, very low velocity distribution, which is typically it converts into microkelvin temperature. So then on top of that, we also utilize the concept of Zeeman shift in presence of an external magnetic field which is non-uniform. These atoms experience what is called the Zeeman shift of their energy level or magnetic force on this atom, because these atoms can also be considered as tiny magnets, and this optical and magnetic force together constitute what is known as magneto-optical trap. And then using this magneto-optical trap in presence of an inhomogeneous magnetic field, which is also controlled and created in the lab, as well as the laser light which are perfectly tuned, we can create very reliably a large sample of cold atom. Here that white region is just the fluorescence coming out of a large number of atoms in the lab. And for example, here again you can see some other atom like potassium atom, but the atom fluorescence is so large typically that it can be captured using a simple mobile camera. So this is a mobile phone camera picture. Of course, for doing measurements and qubit operations, we do use high-end scientific CCD cameras. So this is one way of creating a bunch of cold atom. Of course, this idea of cooling and trapping atoms, those days it was not very clear whether they can be used for quantum computation. Itself was responsible for a Nobel Prize in Physics, which was given to Professor Claude Cohen-Tannoudji, Professor William Phillips, and Professor Stephen Chu, and for development of methods. So these were very basics for the present day quantum technology. So how do we detect? One way to detecting this atom is to look at the fluorescence. Another way is to do what is called shadow imaging. One can send a light which is resonant with the atoms and then look at the shadow which is created on a CCD image plane. Of course, this is a cartoon which I prepared, but with a large number of lenses, microscope objective, it's very easy to actually capture the shadow of these atoms, and from there we can have lots of information. That means total number of atoms. The temperature estimate can be done by just seeing how fast this atom cloud is expanding once they are released from the trap. Just switching off the trap, that like magnetic field and the laser light, they will simply ballistically expand and then fall under gravity, and that can be easily detected on the CCD camera. So all this information can be found out. So this is part of my lab where you can see all these trapped atoms, and then they can actually be even detected using the techniques what I have explained. So I will not get into too much detail about further cooling process to reduce the atom's temperature and so on. So I'll skip these 2 slides, but I just wanted to highlight what kind of atomic velocity distribution or temperature we are talking about. Typically, for example, in order for these atoms to be trappable in optical tweezer array, which I will describe next, one needs to go down to the temperatures which are listed here, and this is in a log scale. So this is far, far colder than liquid nitrogen temperature or superfluid superconductor temperature, even colder than microwave background temperature, liquid helium temperature, and everything. So, but you know, the other side of it is that it's not that the entire system is cooled down. Only a few atoms which are of use, they are cooled down to such low temperature. That means their velocities are reduced. Okay, so now I will say how these atoms are transferred one atom by one atom into optical tweezer array. So the idea is relatively simple. If you shine a focused laser light and at the focal point, the intensity of the light is very high. And because the intensity is very high, there is a concept called light shift or AC Stark shift, and the AC Stark shift is proportional to the intensity. So as you are shining, let's say, a laser light which is shown at the top in red with a lens, and then at the focal point, since intensity is very high, there is the maximum shift of the energy level of this atom. And then since the atoms are like any other object, would try to minimize the energy, so this is like a trap for them, and the atoms which will naturally go into the deepest point of the trap. Of course, if the atom's kinetic energy is much higher than the depth of the trap, then that will not happen. They will simply fly out. That is why this pre-cooling in the magneto-optical trap is required. And then once this focused light creates a reasonably deep trap, the atoms can then be captured in such a deep trap. For example, this was discovered a long time back with by Arthur Ashkin, but he was given Nobel Prize only in 2018 for optical tweezers. And then optical tweezers are not only for atom trap, for many other activities, but we do use a lot of this atom trapping application of optical tweezer. So I have given an example here. If you take a 10 watts laser which is focused to 100 micrometer, which is relatively easy to do in our lab, with 100 nanometer detuning. The detuning is important because this laser light should not be on resonance, otherwise it itself will knock that cold atom out. So it needs to be very, very far off resonance so that there is no scattering from the atoms. So they are peacefully trapped in the focus. So the trap depth is typically 1 millikelvin, and that is the reason why you have to cool down the atoms or reduce the atom's velocity to below millikelvin, like tens of microkelvin. So once we do these things right, it is rather easy to transfer the atoms into the optical dipole trap. Here one example from one of the labs where I worked earlier, where we can focus the atoms and then we can create a very nice region where this ultra cold trapped atoms in optical tweezers are present. Okay, so this concept is expanded. Now instead of sending one focus light, if there are many focus light which are specially separated, so then each focus one atom will be trapped, and that is how one can have a scalable atom trap system. Okay, so another concept which is relevant here, suppose the focus is very strong. That means typically we do 1 micrometer waist size of the beam by shaping the light using correct microscope objective and so on. And then if there are more than one atom, suppose 2 atoms come, they collide with each other, and the collision between atom causes both of the atoms to go out. So that is why there can be either 1 atom or 0 atom, not 2 or 3 in such kind of trap. So that is one of the reason where we can ensure that there is only 1 atom per lattice side. And how do we create such thing? One way to create using an hologram. So this, for example, is a digital mirrored device. We have also special light modulator, which is a very simple device. We create a programmable hologram on this surface where I'm pointing, and then if you shine laser light onto that surface, whatever shape the surface has is transferred into the shape of the trap. If it is, like dark, bright, so this is very similar way of creating this kind of bright spot, dark spot, bright spot, and dark spot. So that's once it passes through the microscope objective, it creates a very nice array of atoms. So this is one way. For example, we shine onto the cold atom cloud, this shaped trap, and then we can have different regions where the tweezer, it's called tweezer because it acts as a tweezer, only optical tweezer, and then atoms can be trapped. So for example, another way to create using this special light modulator, where we can create whichsoever kind of shape we desire by programming it. and then shining onto this atom, we can create this. So once we have created this shape trap, for example, in this example, which was work done in the MIT Harvard collaboration, I'll show quite a few of the reference of that. So this light is transferred to the atoms which are already cooled, and then this kind of a pattern which is created, where in one of the tweezer there is a trap, maybe some tweezer which is empty, next there is one empty, and then one trapped, and then such a thing. They are very nice, beautiful statistical stochastic loading of qubits, but they are not very convenient for doing operations, because it's very statistical, unreliable which site will have atom. So there is a need for creating a defect-free array. So one of the way to creating a defect-free array is called reconfiguration of trapped atom array. So what is done is that we go from this kind of a situation to this kind of a perfectly aligned atom trap. By the way, this is not a cartoon. This is real data of one black spot is actually one atom. So every black spot is one atom and they are detected. And so typically what is done is that I'll show the idea. Before showing that, we need to also discuss that why there is a need to make this very fast, creating defect-free array, because one reason is that for say, let's say a single atom in the trap is 10-second lifetime. Imagine we have a 100 qubit system, that means 10 by 10 atom. So that means in order for the entire defect-free array, entire 100 qubit quantum computer to remain defect-free, that means there is a probability that one atom will leave the trap in a 100 millisecond kind of time scale. In that 100 millisecond time scale, we have to really make sure that the defect-free array is created for the next quantum computing task, which is not a very time-consuming task. I'll explain later. So there are various algorithms how you do that. So this is typically done by actually plucking one atom from one space by again one tweezer which can move. So there is a device called acousto-optic deflector, which actually, depending on a frequency which is fed into that, which again in our control, can actually take the atom from one trap location to put in any other location. And that's how one can create a very nice array. So I'm just giving one example where you can take an atom and then there are various ways one can actually transfer the atom from one trap location to another. And then by implementing this algorithm, one can very efficiently make sure deterministically that where the atoms can be transferred. And at present in our lab, we are also working closely to optimize this kind of algorithm to create a very nice defect-free array trap. So this is like, if you like, in a classical computer, the transistors are in some kind of arrangement array. In our case, each single atom is acting as a transistor, and once they are prepared this way, so this becomes like a quantum computer platform. Okay, so one more concept I have to introduce. So this is called how to create atom-atom quantum correlation or entanglement. So this is done via what is known as Rydberg excitation. So this concept is also from the physics perspective known for a long time, thanks to Johannes Rydberg. So if one can excite an atom to a very highly excited state, let's say something like at a 50s state, typically, if you take a hydrogen or even sodium and so on, where they are very low lying, energy states, which are of the order of Bohr radius. But once it is taken to very highly excited state, but not to ionize it, that is a different physics. So this is still a neutral atom, but then the electron is orbiting far, far away from the atom. Such atoms are known as Rydberg atoms. And then they have a very interesting property. They have a very strong interaction depending on, if n equal to 50, you can already see 50 to the power 11 divided by r to the power 6, the distance between two atoms, and that kind of a strong atom-atom, Rydberg-atom interaction one can create. And this concept will be very useful in a slide or two when I explain how this is used to create entanglement. So imagine that one is exciting this atom to such a high Rydberg state. So this is typically done using radiation of laser light with correct frequency, so with very low line width. That's another challenge. But once we do that, imagine that in this array, one of the atom is excited to the Rydberg state. If there is another atom which is also excited to the Rydberg state, which is very closely spaced, so their interaction would cause the energy to be shifted heavily. So at the first phase, the laser light is no longer tuned to such a two atom excitation simultaneously when they are side by side. So because that is not possible, but you don't know which particular atom got to the Rydberg state, there is no other way of writing the state as a entangled state, which is one atom is ground, one atom is Rydberg, one atom is Rydberg, one atom is ground state, but without identifying which atom. So that means these two atoms now, their states are totally entangled with respect to each other. If you make measurement on one atom, whether it is in ground state, then you know for sure the other atom is in the excited state, and vice versa. So this is like one straightforward way of doing entanglement measurement, bell type measurement, and so on. And people have done these things heavily over the past few years. So we have also done many Rydberg excitation schemes. So there are something called electromagnetically induced transparency way of creating and detecting Rydberg excitation, and then many details will be present. All right, so now that once we can do this Rydberg excitation, so what's next? So in our system, that pathway what we are taking is that we have this bunch of atoms in optical tweezer arrays, and then we shine two photons, one photon with energy of 1013 nanometer, another with 420 nanometer, and then using these two photon we can create a Rydberg excitation at a 70A state. So now this is already high enough Rydberg state to do entanglement generation between atoms in the array. All right, so once this is done using the Rydberg excitation, we can coherently couple the state 1 to the Rydberg state, and then the hyperfine ground state separation are identified as that famous 0 and 1, which is the qubit states. So if we can now manipulate the state between 0 and 1, then our job is done. So this is typically done by, I'll first say that and then come back to. So this is typically done by sending another laser light, which is actually transferring the atom between state 0 and 1. And these two atoms are known as control and target atoms. So you make a state change in one atom and detect using another atom. And in particular, the rubidium atom platform, this is done using a 795 nanometer laser, which passes through a device called electro-optic modulator. And this device actually creates this two Raman beam, which are shining between the two energy level, which is called 0 and 1. Okay, and then using this, the qubits are encoded in two hyperfine ground state, and f equal to 1, mf equal to 0, f equal to 2, mf equal to 0. These states are magnetically insensitive clock states because we have purposefully chosen them to be in magnetic substate 0, and the transition between them are also microwave forbidden directly, so they are driven optically via this Raman transition. The Raman transition ensures that the atoms undergo transition without getting kicked out of the trap, unlike the use of the direct transition using resonant frequencies. So this is how how one is doing that. It is tuned to one of the transitions in rubidium, and then single qubit gate operations are achieved by pulsing the laser light for a certain time. For example, once we fix the frequency intensity of the laser, then there is a concept of pi pulse. Pi pulse can transfer the atom population from, let's say, this state 0 to state 1 completely. There is also another concept of pi by 2 pulse, which can create a equal superposition of state 0 and state 1. So the entire exercise now reduced to a series of pi and pi by 2 pulses, how to create all these gate operations. For example, if you send a pi pulse to a state of 0 atom and transfer it to 1 atom, this is amount to be with some phase connection, some kind of CNOT gate, and many such operations which are followed. So there are many composite gates. For example, there is Hadamard gate, which is Raman laser pulse duration of pi by 2 omega. Omega is the Rabi frequency in this case. That means it's a measure of the intensity. There are also S gate and T gate. For example, as I explained, phase accumulation, pi by 2 phase accumulation between the two state, and then we can do a far detuned Raman phase accumulation, which is a pi by 4 range. So all one is saying is that now having these atoms, creating the entanglement between the atom, we can really create various type of gate operations, and which are practically implemented in present day. All right, so I had already explained you how this Rydberg excitation with 420 and 1013 nanometer lasers are done. The complexity is that these lasers have to be very narrow line width. The relative phase noise between the lasers are at a Hertz level, which is not, that's not why, not everyone is creating these atomic qubits on a daily basis, but technology is progressing at such a fast rate that this kind of technical challenges are getting resolved. All right, so one of the way, once we create this entanglement, as I had showed, once the atoms are close to each other, one shines the Rydberg laser, and then also I explained that this focus or the focus laser light, which is trapping them at the first place, they can also be moved around using this acoustoptic deflector. So they can also be physically moved around from less than 5 micrometer to around 100 or more micrometer. And then once they are moved around, the entanglement still remains. And this transported entanglement, and one can actually do gate operation, and people have again showed them few years ago that by slowly moving these atoms, slow means not that slow, but still of the order of a meter per second kind of a speed, one can still maintain the Bell state fidelity at a very high level, because atom fidelities now people are talking about 99.99, 99.999%. So that is how the gate operations are also controlled. And there are also very nice way. Again, I am showing one of the publications which were recently done, where this tweezer trapped array have been moved around, and then also the addressing was done. And from the camera counts, one can also see that whether there are 0 atom and 1 atom in the trap. And that means once we can detect 1 atom, we can also detect in which particular quantum state the atom is, whether it's in state 0 or state 1. So all the technical aspects are done. Rydberg excitation and transporting entanglement, these are also relatively recent publications. So you can read more detail about the work, what is done here. And this is how there is the entangling zone, as I explained. There is also the storage zone where the defect-free array is created, and there is also a zone where the atoms are transferred, where they are imaged onto the CCD camera using the microscope objective. So this is another pictorial description. For example, this is how in real time the atoms are moved around, as you can follow the video. And this is real data where the entanglement generation and then gate operations are performed, and then eventually sent to a readout zone where a pulse of light actually allows them to be seen on the camera. All right. So now just one more topic I wanted to highlight, that this is like a traditional digital computation or universal quantum computation, but this atom traps also allows for what is called this analog quantum computing, or what is also known as quantum simulation. So typically, for example, when we create a defect-free array and then create an entanglement by sending this atom to Rydberg state, then because the Rydberg atoms have dipole-dipole interaction, given their original arrangement, whether it's a square lattice or a triangular lattice or a hexagonal lattice, and when the interaction is switched on, interaction is typically indicated by this term in the Hamiltonian, and then they would normally make a situation where you may have one atom, another empty space, one atom, another empty space, and this is also geometry dependent. So this is like directly observing the unitary evolution of a given engineered Hamiltonian, and this is just one example. There are many other ways actually. Just by taking images of this atom array, one can get into the ground state solution of a very, very complex Hamiltonian. I am not an expert, but I learned that many other domain, including finance, various evolution actually follow complex Hamiltonian evaluation, which can easily be simulated using this kind of an atom trap array. So just wanted to highlight that people have made a lot of progress, and if one is interested, the initial big success of the neutral atom based quantum computing platform was dedicated to the simulation of complex Hamiltonian problem, and this is still a very active field of research and very productive. Okay, so I would like to give a few insights and outlook. For example, one of the biggest problem what we face, of course, as you guessed, is how long to integrate the photons which are emitted from the atoms into the CCD camera to get this beautiful image. If the image is very noisy, it's very easy to understand. One single atom is not fluorescing so many photons, and it's not very easy to kind of detect such an image. This is like a proof of principle experiment, but when one needs to do a real life quantum computing application, then such a slow rate of computing is not going to be very, very attractive. So one of the bottlenecks in this field is how much time it takes to take one single image of this atom array. Typically in this kind of experiment, it takes anywhere between 1 to 10 milliseconds, which is very large, though the gate operations and so on can be very, very fast. They can even be in the microsecond. So we have recently looked into one way how to detect this atomic state very, very fast. So this was also one of the recent paper from our group. So where what we do is that we shine a laser light, another one, through the cloud of atoms in presence of a pair of Raman beam, which is making a spin oscillation between the two states, let's say state 0 and 1, and then we can directly measure the spin oscillation from state 0 and 1, and looking at the time scale of the measurement, they are typically of the microsecond. Even in the frequency space, it's a very sharp distinguishing feature. So we know that whether the atom is in hyperfine state 1 or hyperfine state 2, which actually allows us for a much faster detection. We have benchmarked this detection to actually see whether we can detect very small number of atoms. This is like a detection of around 10 atoms. This is like a detection of 70 atoms in that trapping volume. And we are trying to push for now going for a single atom detection. This, for example, on the contrary, when there are no atoms, so that means you can clearly see that the signal is very distinctive in terms of atom and its state detection. Another direction is that all these optics and optical arrangement, what I have shown is bulk optics. That means, using 1-inch mirror, wave plates, special light modulator, which are of the order of 1 inch size. And typically they easily scale up to hundreds of them. And one direction the world is going, and we are also trying to take, is to miniaturize the optics on photonic integrated circuit, so that the laser light can simply be coupled inside the vacuum chamber on this photonic integrated circuit, and then you can create the trapping laser light for the atoms. Here, for example, you can see all the photonic integrated circuit related trap eventually resulted into this magneto-optical trap, which is shown here at this point. And so here there is a zoomed version of this magneto-optically trapped atom, but this is not done using bulk optics anymore. This is done using the photonic integrated circuit. Similarly, there is also a very recent report in Nature just this month, where this incident light, instead of passing through microscope objective as well as bulk optics, is just through holographic metasurface, and using this holographic metasurface one can create the configurable atom traps, and these things can easily be scaled. For example, these are nanometer sized object, and this can eventually create a very, for example, you can look at the size of the order of 500 nanometer. So one can create a very, very large number of highly dense qubit packed in a small region for further operations. This particular demonstration was done on strontium atom, but the physics is the same to be demonstrated for other atom. Okay, so I think I have kind of come to the end of this introduction. If there are any questions, I would be very happy to answer.
Thank you, Professor.
Okay.
Professor, can you please check the Q&A button at the bottom?
Okay, let me check it. Let me stop share then. All right, so there is one question. Can you kindly repeat how only one atom is trapped during laser cooling process? Okay, I will answer that question. That's a very nice question that will require me to share the screen again. So, all right. So what I think you can see my screen, right? So laser cooling and trapping leads to a bunch of atoms, as you can see here. This, for example, okay. For example, this is the CCD image of the fluorescence of light, typically coming from 100,000 atoms here. That's not one atom. But now what is done is that a separate pattern of light which is created using a special light modulator, and because this is a hologram, and then that is superimposed onto this atom trap. And now what it does is that once we have a very strongly focused laser light, it creates a trap for the atom. In principle, even here, many atoms, more than one atom can be transferred. But if the focus, and that is also true here, this example from my lab, you see, these are actually a large number of atoms transferred to the trap. We have used, yeah, so hello? So on the other hand, suppose if the trap is very tight, extremely tight focused, so in that case what happens, these atoms, if there are two atoms in that small trapping volume, they collide on each other. So this is called collisional escape. So there is a collisional blockade. So if they collide, there is a collisional energy between these atoms, and both of them actually eject out of the trap. So if one atom is in the trap, it is peacefully there. If two atoms or more are there, then they collide out. So this is how we can ensure that there are only one atom in the trap. So that's one way of actually creating one atom in the trap. I hope that this answers the question. Can you explain the difference between analog QC and universal QC? Okay, so universal quantum computing is the traditional gate-based quantum computation. Like in many other platforms, what people are doing, it's very similar to when people say computation, making use of zeros and ones. In case of quantum, of course, making use of the entanglement between the particles as well as the superposition between state 0 and 1. So it allows a lot of advantage. But analog quantum computing is actually another byproduct of this neutral atom based quantum computing platform. Just the very structure of this atom trap is dependent on the interaction between atoms, which we can tune. So this is like once you write the Hamiltonian, where you write the kinetic energy of the atom, potential energy of the atom, and then its solution for a large number of atom is not a trivial solution. But in our case, since it's like a trivial solution in the sense we can simply take an image of the entire ensemble after we introduce this interaction. So that means after running or evolving the quantum system, so we can actually now compare the CCD image of this atom trap, and that's actually a solution. And that solution, if you want to do a classical computation, for example, if it is a solution of a complex spin model or something like it, it's nearly impossible if the atom number increases even beyond some few tens or something like that. But in our case, we can even do this for hundreds and thousands of atoms, and this is like a analog way of solving the problem. So that's why we call it analog quantum computation. There is another question: can two entangled atoms be trapped like one atom trapping? Well, typically, once the atom is trapped and then the entanglement is generated momentarily by pulsing the Rydberg lasers, and the trap is for a short time switched off. But then once the entanglement is generated, then it can be transferred back to the trap and can be moved around, like I showed in one of the slides. And it is shown that even after the atoms are moved very, very far away with respect to initial position, so the entanglement is preserved. So if your question is that can two entangled atoms be trapped like one atom trapping? In a way, yes, but not probably the classical picture you might have in mind. Okay, so that's a rather complex concept. There is one question: what are the challenges and limitations to make quantum computer based on neutral atom? Okay, I hope that the entire talk was based on challenges and limitations as well. See, one is that all these lasers and creating the trapping geometry, taking images of these atoms, doing a very nice analysis and state detection. So these are all challenges. I worked with neutral atom quantum computing, so I would not like to talk too much about limitations. So there are advantages and disadvantages I have actually highlighted in one of the slides. So as such, there is no, I would not say limitation. Of course, in a bigger context, if one wants to see that where is the world in quantum computation, how many qubits are presently demonstrated, and how much is error rate there, and whether that is enough to break the RSA codes and so on. So this is no for any platform, not just neutral atom based quantum computing, but neutral atom based quantum computing are one of the fastest growing platform. Over the last few years, there had been a huge scaling and other aspects done. So this is very encouraging. So how does the quantum error correction scale with qubit count? It's more to do with what are the fidelity. For example, in our context, how well you know A, the initial state preparation, B, when we do a pi by 2 pi pulse sequence, what is the final state preparation, and then how well we can detect which state the atom is there. So that all contributes to the error. So present atom trap based state of the art errors are of the order of 1 part in 10 to the power 4 or going to 1 part in 10 to the power 5. And then of course the quantum the process. So what is the threshold theorem in fault tolerant quantum computing? Yeah, I am not an expert. I think the people in algorithm and so on would be able to answer this. Are variational quantum algorithms practically outperforming classical heuristics? I would say yes, but again, I am not an expert on algorithms. I am more of a hardware person. So, but I would tend to give the answer that it is yes. How do tensor network methods compare to quantum hardware for certain problems? Again, this is a little bit beyond the scope of the neutral atom based hardware installation. But on the other hand, that the universal quantum computing is in general capable of handling in any platform. So, but on the other hand, again, so how does quantum computing impact modern cryptography? Yeah, it impacts in a very profound way. For example, yeah. So
That's it, Professor. Thank you.
Okay, excellent.
It was a very good talk. Thank you. Thanks a lot.
Thank
so
you.
extended, it got a bit extended also, and that on a weekend.
I see. Okay,
So,
thank you
thank
to the
you.
participants for patiently listening. I hope that I could transfer some ideas and implementations. Thank you.
Thank you, Professor.
Thank you. Bye bye.
Soumya?
Yes,
No,
sir.
Professor, you may leave. Soumya, please take over.
Yes, sir. Yeah, hello all. We would like to invite few feedbacks. Kindly raise your hands. We will let you to unmute and also please switch on the video if you can.
Participants, the quiz link has been posted in the chat box. You may please attend it, okay? I'll not be sending the mail separately.
So is anyone willing to share the feedback? You can unmute and please go ahead. Yes, I can see Anuj. Please unmute yourself.
Yeah,
Thank you, sir. Yes, sir, you're audible, sir.
Yeah, I would say this complete workshop was exceptionally well structured. I would say like covering foundation not only in quantum physics, hardware implementation, and the operator formalism was also discussed, and not only restricted to most of the workshop which I have actually attended earlier. I've seen talking about one single modality. But I think coverage of the other modality of quantum dots, spin qubits, neutral atom, photonic quantum computing, and that too from the NQM perspective, I think that was really insightful. And I would also appreciate the daily quizzes, which enhance engagement and reinforce the conceptual clarity as well. Congratulations, and I appreciate the efforts which has been invested by your team. Thank you.
Thank you, sir. Thank you very much. Shri Maya, please go ahead.
Um, Hi, I'm Srimay. So I have also attended the I have attended the first workshop that you conducted, and this is the second one. And I can say these two workshops have been very valuable for me, for somebody who is interested in working on the hardware side and wants to actively contribute to the country's growth in this quantum arena. I think it is a great start. I mean, at least the good thing is that we could see the at a glance what is the National Quantum Mission and what are the components of it. Then a little bit about each modalities and things of the video of the like departments involved in it, and it is like it widened my knowledge and also helped me to identify different topics that I could focus on. So I'd like to congratulate you for conducting such beautiful workshops, like the first one and the second one. And I sincerely am grateful to the FQCI. I hope that this series continues on, and maybe future you can focus on like different verticals of the mission, more specific about each modalities like algorithms or superconducting qubits, semiconducting qubits, workshops focused on that. In that way, I think this will be like we can make the knowledge accessible to people. We can to all our students in India, and we can also help them to come into this field, and that will encourage them to contribute to the field, to India's quantum mission, as because there are a lot of hypes and lot of things. As a beginner, we really cannot discriminate, and these sessions help us to focus on and choose the right thing. So congratulations, Soumya and Dr. Ramashankar. I hope you continue this session in the future. Thank you so much.
Thank you for your.
Thank you. Srimaya, just to add to your point, whatever you said, this is just a familiarization workshop. We will be conducting an advanced level workshop also. So wherein that is going to be specific to like say superconducting, semiconducting and all. And you'll be given some hands-on training sessions also will be conducted in that. Okay.
Hello, ma'am. Hello, sir.
So go ahead.
Yes, sir. Yeah, please go ahead. We could hear someone speaking.
Yes, ma'am. Can I also share my feedback because my
Yes.
chat is disabled?
Sure, you can go ahead.
Okay. Hello, everyone. This session was very interactive. I found a lot of things to explore in this field, and also the sessions were well structured. I got to know a lot about the photonics, the qubits, superconducting qubits, etc. And the instructors were very smart, and the way they delivered the knowledge was excellent. I am also doing my work on the quantum machine learning at IIT Indore. So I found it very helpful for me. Thank you.
Thank you. Shushanta, please go ahead. Sorry, sir, you're on mute. Can you please unmute your slide? Sorry, sir, you're not audible.